All right, today we're jumping into one of the most important papers in AI history. We're talking about deep residual learning, but you probably know it as a ResNet, and it completely, and I mean completely, changed the game. So let me start with a question for you. When it comes to artificial intelligence, is deeper always better? For years, pretty much everyone in the field would have shouted yes from the rooftops. But what if it's not that simple? What if the one trick everyone was using to make their models smarter was actually making them dumber? I mean, the logic made perfect sense, right? You think about how our own brains work with all these layers of processing. The idea was to just copy that, keep stacking more and more layers in a neural network, and it should be able to learn more and more complex things. Going from seeing simple edges to shapes to really intricate patterns. And for a while, man, it worked like a charm. But then they hit a brick wall, a really, really weird one. As they built these networks deeper and deeper, expecting better and better results, something totally bizarre started happening. As this quote from the paper itself says, the accuracy didn't just level off, it started to degrade. It actually got worse. And for the AI community, this was a massive shock. It just didn't make any sense. And let's be super clear here. This wasn't the usual suspect, overfitting, where a model gets good at its training data but fails on new stuff. No, this was way stranger. These super deep models were failing on the exact same data they were trained on. Think about that. It's like studying for a test and then getting an F on that very test. They called it the degradation problem, and honestly, it was a total mystery. Just look at this chart from their experiments. It lays the whole problem out, plain as day. The 56-layer network, it has a higher error rate than the much shallower 20-layer one. It's right there, in black and white. More layers were literally causing more mistakes. How on earth is that possible? So this completely baffling result leads us right to the heart of the mystery. It's this logical puzzle that just had everyone scratching their heads. And the question they were asking was actually pretty simple when you think about it. If you already have a shallow network that's working great, why can't a deeper version at least match it? Why can't all those extra layers you added just learn to do, well, nothing at all? Okay, let's walk through this together. Imagine you've got a shallow network that's working perfectly. Step 1. Now, step 2, you just tack on a few extra layers. In theory, those new layers could just learn what's called an identity mapping, which is just a fancy way of saying they do nothing. They just let the signal pass straight through unchanged. If they can do that, then the bigger, deeper model should, at the absolute worst, perform exactly the same as the shallow one. It should never be worse. It just doesn't make any sense for it to be. But that's exactly where things got stuck. The logic was flawless, but in the real world, it just wasn't happening. For some reason, the algorithms that we use to train these networks found it almost impossible to teach a layer to do that one simple thing, just pass the information along. Optimizing for nothing turned out to be incredibly hard.
And this is where the genius of this paper really shines through. The researchers had this incredible aha moment. They didn't try to brute force a solution. Instead, they completely reframed the problem.
So check this out. The old way was trying to force a network layer to learn the entire complex final output all by itself, from scratch. We'll call that h of x. The new idea was so much more elegant. They said, forget that. Instead of learning the whole thing, what if we just teach the layer to learn the difference, the small adjustment that's needed? We can call that f of x. And then you just add that little adjustment back to the original input. It's the difference between painting a masterpiece from a blank canvas versus just doing a few touch-ups. It's way, way easier. And here's the core idea right from the paper itself. They basically said, hey, we bet it's just plain easier for a network to learn this small change, this residual, than it is to learn the entire mapping from scratch. It was a fundamental shift in thinking. So how did they actually pull this off? Well, they used a beautifully simple, elegant piece of architecture. They called it a shortcut connection. Let's build one of these residual blocks right now. First up, you've got your input signal. Let's call it X. It goes into a couple of processing layers, just like in any normal neural network. But here's the twist. These layers have a totally new job. They're not trying to figure out the final answer. Their only mission is to learn that change, that little adjustment we talked about, the f of x. Okay, now, while all that is happening, the original input, x, does something really cool. It completely skips those processing layers. It takes a detour, a separate express lane. And that is the shortcut. And here is where the magic happens. At the end, you just take the output from the layers, that little adjustment, f of x, and you add it right back to the original x that came whizzing through the shortcut. The final result is just the original input plus the change. So what happens if the best change is no change? The layers just learn to output 0, and the original signal passes through completely untouched. That whole impossible identity problem, solved. It's just genius. So, the million-dollar question. Did this simple, clever idea actually work in practice? Oh yeah, it worked. And the results weren't just good, they were absolutely revolutionary. Take a look at this table. It tells you everything you need to know. For the plain old network, going from 18 to 34 layers made the error rate go up. It actually got worse. But for the ResNet, going deeper made it dramatically better. That degradation problem wasn't just fixed, it was completely turned on its head. This little shortcut basically blew the doors wide open. It allowed researchers to build networks that were deeper than anyone had ever imagined. The model that won the big competition that year, it wasn't 30 layers, it wasn't 50 layers, it was 152 layers deep. Let that sink in for a second. That's 8 times deeper than the previous champion network, VGG. But here's the kicker. Because of this new efficient design, it was actually less complex to compute. So you got deeper, you got better performance, and it was more efficient. That's the holy trinity right there.
So you really can't overstate how huge this was. ResNet didn't just win a competition. It laid down a whole new foundation for pretty much the entire field of deep learning.
In 2015, they didn't just win the main event, the big image classification contest. They won everything. Object detection, first place. Object localization, first place. Object segmentation, first place. It was a complete and total clean sweep. Overnight, ResNet became the new gold standard that everyone had to use. When you step back, the story of ResNet is just an amazing lesson. It shows that the biggest breakthroughs don't always come from adding more and more complexity. Sometimes they come from a simple, elegant change in how you look at the problem. And it really makes you wonder, doesn't it? What other impossible problems out there are just one clever little shortcut away from being solved?